Chapter 8, which is on sets and inequalities. And so let's start section 8.1, sets, basic terms, and notation. Okay, so first off, a set. A set is a well-defined collection of objects. And so elements. The objects which form a set are called elements or members of the set. So we denote that, let's say X is a member of the set A by the following notation. X is a member of the set A. And so is a member of. So that little object here denotes the fact that this is a member of a particular set. So there are several different ways of uh, writing a set. So the listing method. So one way is just to write out to list the members of the set, such as 1, 3, 8, 12. Those are members of a set. Those are the members of your particular set. When you write, when you list out your members of your set, order does not matter. So order the order of this list of members in a set um, does not matter. And the fact if they are listed more than once, well, I guess, and neither does redundancy. So thus 1, 2 is the same as 2, 1. So the fact that they're written, in a different order doesn't make any difference. And is the same as 1, 2, 1. So in general, um, we try to write it in order, just so that it looks nice, uh, and you know, because we're human, and we try to write it without duplication. You can have no members of a set. So the empty set. The empty set, denoted by this symbol, or just by that symbol, is the set which contains no members. Okay, so you could have a set that has nothing in it, and so that's called the empty set. You could also have an infinite set. So a finite set, so a set is finite if it contains a finite number of elements. For example, the set 1, 8, 14. Okay. You could also have an infinite set. So a set is infinite if it contains an infinite number of elements. For example, the set 2, 3, 4, etc. And so 2, 3, and then continuing forever. Um, these are called ellipses, and this means continue with the same pattern. They need even more room. Okay, so those three little dots mean continue with the same sort of pattern that I've given. Okay, so let me do some examples on page 327. Let me do problem number 2. The set of the first 5 odd natural numbers. In exercises 1 through 20, list the elements of the set. And so, 1, 3, 5, 7, 9 is the list of the first 5 odd natural numbers. Let me do problem number 8. The set of all even integers between 3 and 11. And so let's list these. And so 4, 6, 8, and 10 are all of the even integers between 3 and 11. Okay, so now uh, let me do problem number 10, but first let me tell you the set building notation. So another way to write a set is in set builder notation. So in set builder notation, you usually have the variable and then either a line or a colon and then some sort of statement involving your letter, your variable, describing your set. And so this means the set of all x of all, and then this means such that. So the set of all x such that whatever. Let's do problem number 10. The set of all x such that x is an odd natural number less than 12. And so let's list these. So odd natural numbers less than 12, odd. 1, 3, 5, 7, 9, 11 is a set of all odd natural numbers less than 12. Let me do problem number 12. Yes. So you can either write it with a colon or this little bar, and they both mean the same thing. And I use them interchangeably. 12. The set of all m such that m is the name, is a name of the month whose name begins with 12, A or J. And so January, April, June, July, August. I think that's it. January, February, March, April, May, June, July, August, September, October, November, December. Okay. And so those are all months beginning with A or J. Problem number 16. No, it doesn't have to be in any sort of order. So I just happen to have written it in this order just because I'm human. And if I didn't write in that order, I might skip one of the members in my set. 16. The set of all n such that n is a natural number multiple of 3. And so in this case, the multiples of 3 are 3, 6, 9, 12, etc. And so I'll just use these ellipses to denote the fact that we continue with the same pattern, in this case forever. Let me do problem number 20. The set of all x such that x is a real number whose absolute value is 7. And so in this case, well, it could either equal -7, because the absolute value of -7 is 7, or +7. And so in this particular case, there are two members of the set. Suppose I ask you, is the collection of all numbers approximately equal to pi a set? And the answer is no. The reason for that is because it is not well defined. Because you are not, since I did not give a good definition to what I mean by approximate, then you cannot determine the exact membership in this set, in this collection. Therefore, that collection is not a set. Let me do problem number 22. 5, 7, 11, 13. In exercises 21 through 30, write the set in set builder form. And so, oh, pi can be in the set, but, and so the reason that this is not a set is because it is not well defined. So this is not well defined, meaning that since I said it's a collection of objects approximately equal to pi, since I don't know what approximately means, you know, 3, who knows if 3 is in that set or 3.14 or whatever, because I haven't told you what approximately means. And so that's why. Well, maybe 22 over 7 is in it, but you know, maybe I wanted to be more precise. Maybe I mean approximately. Uh, I'm saying, well, you have to be approximately. In my case, so you have to be correct to 1,000 decimal places. So in which case, then 22 over 7 would not be in that set. So I don't know if it's in the set or not because it depends on what I mean by approximately. Since I don't know what it means by approximately, then I do not know what the members of the set are. So I can't tell you, you know, what it's equal to. Well, if you just say the set containing the member pi, then pi is in the set. If you say the number, the set, the collection of objects approximately equal pi, then no, it will not be a set because you don't know what approximately means. Okay? Okay, problem 22. Let's write this in set builder notation. And so this is the set of all x such that x is a prime number between 4 and 14. So that could be a description of that set. Let's do problem 26. 1, 9, 25, 49, etc. And so this is a set of all, well, squares and numbers such that, well, x is a natural number. We could also write it as set of all x squared such that x is a natural number. Either way is perfectly fine. And so, wait, 1, 3, 5, you stupid. Odd natural number is an odd natural number. Not any natural number, it's an odd natural number. So, because it's 1 squared, 3 squared, 5 squared, 7 squared is an odd natural number. So, we could also write it that way, I guess. Um, let's see. Oh, okay, so let me do some additional notation. What are those letters at the end? Ah, so actually, let me give you, uh, let's recall some things, some number sets. Uh, and so this is natural numbers, whole numbers, um, integers, rational numbers. Yes, it was the whole number symbol. Mm-hmm. Yes. um, rational numbers. The set of all PQ such that P is an integer and Q is a natural number. Um, there's a set of irrationals. Well, R is a set of real numbers, and this denotes a set of irrational numbers. Okay, so those were all the number sets. Okay, subsets. Oh, and so this would denote the even numbers, because it's 2 times the set 1, 2, 3, etc. So this is the set 2, 4, 6, because you're multiplying everything by 2. Similarly, 2 times the whole numbers plus 1 is, well, 2 times the set 0, 1, 2, etc. plus 1, which is 0, 2, 4, etc. plus 1, which is add 1 to everything, so 1, 3, 5, 7, etc. The odd numbers. So I just sort of wrote in notation odd natural number as in that fashion. Okay. Okay, so let's see. Subsets. So let A and B be sets. I'll denote the fact that A is a subset of B. Um, and this is defined as follows. So A is a subset of B if X is a member of A implies that X is a member of B. So A is a subset of B if every member of A is a member of B. And so this A here is a subset of B. Superset. A is a superset of B if B is a subset of A. Equality. A is equal to B if A is a subset of B and B is a subset of A. proper subset? A is a proper subset of B if A is a subset of B and A is not the same as B. Oops. Proper superset. A is a superset, proper superset of B if B is a proper subset of A. Okay. Yeah, so you can think of uh, A is a subset of B as being, well, A has less members of B. And so, um, yeah, it's sort of small. So that's why that symbol sort of looks like a like less than or equal to symbol or less than symbol. Okay. Oh, I guess I should have said that. By the way, sometimes the empty set is called the null set. I should have said that also. Null set. Those mean the same thing. To distinguish that C is actually a proper subset, not a variable. Oh, right. So usually when we write sets, we usually write sets in as capital, and the variables are usually done as lowercase. That's a usual sort of way in our notation that we usually put things. Okay. Um, so I guess note the following. Every set is a subset of itself. For every set A. Null set. So it was the null set. So sometimes we call that the empty set the null set. So the empty set, the null set, is a subset of every set. So sometimes I call this the null set. Yep, null set, correct. Hmm. Okay. Union. So suppose A and B are two sets, then A union B is defined as the set of all elements in A or in B. And so let's say that this is A and this is B. Then this good. Oops. So this is A union B. Intersection. And so A intersect B, set of all x, such that x is in A and x is in B. Oh, I should say this is mathematical or, this is mathematical and. And so, suppose that this is the set A, this is the set B, then this is the set A intersect B, the overlap. And so the union is found by just combining these two sets into one larger set containing the members of each of these two sets, whereas the intersection is the overlap between these two sets. So what members are in common? So you only include those members of the two sets that are in common with both sets. Okay, let me do some examples. Actually, well, yeah, let me do some examples first. Then I'll give you some properties. Okay, so let me do first problem 31. Two, three, one, subset of 1, 3, 2. In exercises 31 through 36, identify whether the statement is true or false. So, is the set 2, 3, 1 a subset of the set containing the elements 1, 3, 2? The answer is true, because every element in the set is an element of the other set. So 2 is an element of the set, 3 is an element of this set, and 1 is an element of the set. So therefore, yes, that is true. B, 2, 3, 1 is a set containing the members 2, 3, 1 not equal to 1, 3, 2. That is false. The set 2, 3, 1 is identical to the set 1, 3, 2. Remember, order doesn't make any difference. And so in this case, 2, 3, 1 is a subset of 1, 3, 2. And 1, 3, 2 is a subset of 2, 3, 1. Therefore, they're equal. And so the statement not equal is false. C. 2, 3, 1 is the set 2, 3, 1 a member of the set 1, 3, 2? That is false. Because the set 2, 3, 1 is not a member of this set. The only members of this set are the numbers 1, 3, and 2, not this set. So note that oh, let's say 5, 2, 3, 1, 4. That would be a true statement. So uh, if I wanted the whole set 2, 3, 1 to be a member of a set, then I have to list it. So notice that in this case, so this would be true because this whole set here is in this set. So that would be okay. But otherwise, in this part C, the set 2, 3, 1 is not a member of this set because the only members of the set is the number 1. So that's not a set, 2, 3, 1. 3, and that is not the set 2, 3, 1. 2, and that is again not the set 2, 3, 1. D. Um, is 2, 3, 1 not a subset of 1, 3, 2? Yes, to be a set, order does not matter. So order does not matter. And so when we have a set, order does not matter. Yes, there it is. So in this set, order doesn't matter. So however you list elements, order doesn't make any difference. Okay? So the reason that, the reason that this was not a member of the set is because this whole set was not included in the listing of the elements of the set. Correct. That's right. And so, yes, that is correct. And so, if you just had, you know, a whole list of numbers, then no, because that so the set that you wrote here, 2, 3, 1, 1, 2, is just the same as the set 1, 1, 2, 3. Mm-hmm. Then then those then yes, 2, 3, 1 would be a member of the set. Yep. Doesn't matter if you have some extra. So usually we don't write the duplicates because it doesn't make any difference, and so you don't write duplicates. But duplicates don't matter. Okay. So the fact that you wrote a the number 2 twice doesn't make any difference. It's still the same set. Okay. Let me do problem 32. Right. The fact that and so um, yes, that's correct. Yeah, that's what I was trying to say. So, not necessarily the same number. Okay, so let's see if so 2, 3, 1, 2 is the same as 1, 2, 3. So right, so these are still so these are both sets and they're both equal. Is that what you were asking? So these are both equal sets. Okay, let me do problem 30, yes. That's right. So duplicates doesn't matter. Okay, so let's see that. So the first set is, ooh, no. Ah, that's what you're saying. So no, it's false. That would be false. So that's a false statement. So if it was there was an 8 here, then these are not the same. Right. Yeah. So they have to have the same elements. Okay. Yeah, for two sets to be equal, they have to contain the same elements. 32. 4, 5, 3. Is that a subset of the set 3, 5, 4? Well, 4. So I want to see, is this set a subset of this set? Well, this set is a subset of this set if every member of the first set is a member of the second set. Well, is 4 a member of this set? Yes. Is 5 a member of this set? Yes. Is 3 a member of this set? Yes. So therefore, yes, this is a true statement. B. 4, 5, 3. Is it not equal to 3, 5, 4? Well, 4, 5, and 3, the set containing the members 4, 5, 3 is the same as the set containing the members 3, 5, 4. So they're equal. So not equal is a false statement. C. 4, 5, 3. Is this a member of the set 3, 5, 4? Again, this is false because this set here, containing the members 3, 5, 4, does not contain a set containing the members 4, 5, 3. And so that's false. It contains this set here on the left, on the right, I'm sorry, only contains numbers. It does not contain any sets. So that's a false statement. D. Is the set 4, 5, 3 a subset of the set 3, 5, 4? Oh, not a subset. Well, it is a subset, so therefore this is false. Oh, you know what? That's false. I forgot to write the answer to D. Okay, let's do problem 33. A. Is the empty set a member of every set? Well, that's false. If I look at this set, it doesn't contain the empty set, so that's a false statement. B. Is is it idempotent? Is every set a subset of itself? Well, that's certainly a true statement. Every member of A is a member of A. And so, since every member of A is a member of A, then it is a subset. Okay, let me do part C. Is 2 a subset of the set 1, 2, 3? Well, is every member of this set a member of uh, the set containing the elements 1, 2, 3? Well, 2 is not a set, and so this is certainly a false statement because there are no members of the set because it's not a set. 34. Is the empty set a subset of every set? And that is true. Is every member of the empty set? Well, there are no members. A member of the set A? Well, true, because there are no members in the empty set. Is every set a subset of the empty set? No. If A has actually a member, at least if A has at least one member, then it's not in the empty set because the empty set contains no members. So that's certainly a false statement. C. Is the null set a member of the set containing the null set? Well, that's certainly a true statement because, well, there it is. So is this in here? Well, sure, there it is right there. So that's certainly a true statement. So the empty set could be a member of a set. It's right there. It's a member of that set. Let me do problem number 35. A. Is the empty set a subset of the set of all vowels in the English alphabet? Well, that's true because, well, that's better. And so that's true because the empty set contains no member. Therefore, every member of it is a member of the set of all vowels in the English language by default. B. Is the empty set, is the null set, a member of the set of all states in the United States? That's false. The null set is not a state in the United States. C. The set of all weekdays is a subset. Why is it false? Ah, so the set, so note, so the set of all states in the United States, well, that's just, things like, I don't know, Alabama, Alaska, etc., up to, I don't know, Wyoming. So So all these sort of states, right? But none of them, you know, is the empty set, is the null set. The null set is not a state in the United States. Yep, that is correct, because there's no state in the United States that's the empty set. Mm-hmm. Or maybe C, 35. The set of all weekdays is a subset of the set of all months. Okay. This is false. So if you look at the set of all weekdays, this is like Monday, Sunday, etc. The set of all months, January, etc. And so Monday, etc. Those are not months, and so Monday is not part of the list of January, February. It's not in that list, and so therefore, none of these days here are months. And so, no, the set of all weekdays is not a subset of the set of all months. 36 is the empty set a subset of the set of all of of the English alphabet. Okay, well, that's false. Oh, that's true. What am I talking about? That's a true statement. Every member of the null set is in this set because, well, the null set does not contain any members. Therefore, by default, uh, it is in this set. So that's a true statement. B. Is the empty set a member of the set of all cities in the United States? And so this is false because the null set is not a city in the United States. C. The set of weekdays starting with the letter T is a subset of the set of all weekdays. And that's true because, well, Tuesday and Thursday are days of, are uh, days of the week, and so they are weekdays. So that's a true statement. Okay, so let me do 37. In exercises 37 through 41, compute the indicated set operations using the following sets. A, 1, 3, 7, 13, 21. 1, 3, 5, 7, 9, 11. C. 3, 5, 7, 11, 13. And so let me do part A, which is A union B. And so let's see what is in either A or B. So 1, 3, 5, 7, 9, 11, 13, and 21 are in sets A or in set B. Oh, let me move this over a little bit so I can fix that. There. Okay. Let me do 38. A union C. So what's in A? 1, 3, or C, 5, 7, 11, 13, 21. So 1, 3, 5, 7, 11, 13, and 21. Okay. That's in the union. 39. B intersects C. And so what is in B and C simultaneously? And so 3, 5, and 7, and 11. 3, 5, 7, 11 are in both B and C. So 3, 5, 7, 11. 40. A intersect B union C. So first let's determine B union C. And so B union C, what's in B or C? So 1, 3, 5, 7, 9, 11, 13. So 1, 3, 5, 7, 9, 11, 13 is in B union C. And what is in A and B union C simultaneously? So 1 is in A and this set 3. 7 is in both sets, and so is 13. So you want to determine what's in both sets. So 1, 3, 7, 13. 41. C intersect A union B. So A union B is 1, 3, 5, 7, 9, 11, 13, 21. And let's see what the overlap is between that set and the set C. So in the set C, there's a 3, there's a 5, there's a 7, there's an 11, and there's a 13. Except for the 1. Oh, no, actually, it is everything. 3, 5, 7, 11. Yeah, it's everything. So it is everything, yeah. Let me do problem number 42. And so in exercises 42 through 46, compute the indicated set operations using the following sets. So A is equal to, okay. Oh, it's still, okay, good, good. I was just checking something. Uh, okay. So A is equal to 2, 4, 8, 14, 22. B, 2, 4, 6, 8, 10, 12. Yes. 22, not, okay. 22, not 33. Okay. C, 4, 6, 8, 11. 42, A union B. So, yes, for the union in either set. And so, for the union, it's either set. And so this, in this case, it's going to include 2, 4, 6, 8, 10, 12, 14, 22. So it'll include any number in either of those sets. So 2, 4, 6, 8, 10, 12, 14, 22. 44. Actually 43. No, 44. B intersects C. And so what's in both B and C? So 4, 6, 8. 45. A intersect B union C. So let's determine B union C. And so what's in either? So let's combine these two sets, B and C. So 2, 4, 6, 8, 10, 11, 12. So I'm joining these two sets together. So 2, 4, 6, 8, 10, 11, 12. Now let's find the overlap between that set and the set A. So what's in, so 2 is in both sets. Yes, you really should write what's in the parentheses. You should do what's in the parentheses first before you. So always do what's in the parentheses. Okay. So let's find the overlap between these sets. So 2 is in both sets. So is 4. 6 is not, but 8 is. 10, 11, and 12 are not. So that's it. So only 2, 4, and 8 are in both sets. Let me do problem number 46. C intersect A union B. So let's determine A union B. And so that's the set 2, 4, 6, 8, 10, 12, 14, 22. And that, now let me do the intersection. So C intersect A union B. So let's determine the overlap. So 4 is in both sets, so is 6. So is 8. Oh, and that's it. 11 is not. So 4, 6, 8. Okay. Let me do problem number 47. In exercises 47 through 50, compute the indicated set operations where S is the set of letters in the word send, E is a letter in is a set of letters in the word empty, EMPTY. T is the set of letters in the word train, TRAIN. 47. Determine S intersect E union T. And so let's first determine E union T. So that's the set E M P T Y. There's already a T, there's no R, there's no A, there's no I or N. A, I, N. Okay, let's determine S intersect E union T. So what's the overlap between this and S? So S, there's no S here, but there is an E, there is an N, there's no D. So just EN. 48. S intersect E intersect T. So first you would do S intersect, so you would go left to right. So in this case, you do the same order of operations that you would do with numbers. So you would actually do first S intersect E. So S intersect E is just E. That's the only intersection between these. So there's no S, no N, no D. Yep. And so now let's do S intersect E intersect T. So what's the overlap between E and the set T? Well, there's nothing. So it's the empty set. 49. S union E union T. And again, well, you should do left or right. It really doesn't matter. Well, I'll just do it without doing it. So what's an S? S, E, N, D. What's in E? E, M, P, T, Y. T, T, R, A, I, N. And that's the union of all those sets. 50. S union E intersect T. E intersect T is, well, let's see. Oops. So what's the overlap between E and T? Well, there's no E, there's no M, there's no P, there's a T, there's no Y. So it's T. The union between S and E intersect T, well, it's S, E, N, D, and T. Okay. Let me do problem number 51. In exercises 51 through 54, compute the indicated set operations where A is the set of letters in the word Atlanta. So Atlanta. A T, so it's ATLANTA. G is the set of letters in the word Georgia. GEORGIA. C is the letters in the word county. COUNTY. 51. A intersect G union C. So G union C is, well, GEORIAC would be, well, COU. I need more space. UNTY. So let's find the intersection between these sets. So let's see. There's an A, T, no L, but there is an N. So ATN. 52. A intersect G intersect C. That is correct. So the empty set, so none of the letters are in all three. There are no letter in common with all three sets. Okay, so let's look here. What's in common with all three sets? So A, no. T, no. L, no. N, no. So this, again, it's the empty set. There's nothing in common in all three sets. 53. A union G union C. So let's just combine all three sets. And so this will be, it's going to be a big set. A, T, L, N, G, E, O, R, I, A, C, O, U, N, T, Y. All the letters in any of the sets, but not all the letters in the alphabet. There are a few that are missing. Yeah, so it's just all the letters. Yeah. hmm Okay, 54. A union G intersects C. So let's determine G intersects C. So what is in both G and C? So G, no. E, no. O, there's an O. No R, no I, no A. So just O. And so let's do A union G intersects C. And so A, T, L, N, O. And that's the union. 55. And so A are multiples of 6, 6, 12, 18, 24, 30, etc. B are multiples of 8, 8, 16, 24, 32, 40, etc. And so, yep. And so so this is going to be A intersect B will just be 24, 48, 72, etc. It is the set of all x, such that x is a multiple of 24. It's just 24 times the natural numbers. Note that 24 is just the least common multiple of 6 and 8. 56. A union B. Well, that's just going to be 6, 8, 12, 16, 18, 24, etc. Set of all x such that x is a multiple of either 6 or 8. Set of all x such that x is a multiple of 6 or x is a multiple of 8. Okay, no real good way to describe that set. 57. In exercises 57 through 58, compute the indicated set operations where A and B are defined as A is a multiple of 4, 8, 12, 16, 20, 24. B, yes, it will be 12. B, 6, 12, 18, 24, 30, etc. And so A intersect B will just be 12, 24, 36, etc. It's just a set of all x such that x is a multiple of 12. Yes. Mm-hmm. And so, again, you note 12 is the least common multiple of 4 and 6. 58. A union B, 4, 6, 8, 12, 16, 18, 20, 24, etc. The set of all x such that x is a multiple of either 4 or 6. So set of all x such that x is a multiple of 4 or x is a multiple of 6. Okay. 60. -1, the closed interval from -1 to 4, union the closed interval 3 to 5. In exercises 59 through 76 complete the indicated set operations between the intervals. And so I have here -1, 3, 4, 5. Okay, so I have the close interval from -1 to 4, the close interval from 3 to 5, and I want to find their union. Therefore, when I find the union, it's just going to be the close interval from -1 to 5. Okay, let me do problem number 62. The open interval -3, 2, union, the open interval 1, 4. And so I have, say, -3, 1, 2, 4. And so let's say we have the open interval from -3 to 2. And from 1 to 4. Therefore, the union will just be the open interval from -3 all the way to 4. Oh, so opposite. Uh, so these are closed intervals. So, well, okay, so this is the open interval from -3 to 4. So note, sorry, I forgot, I gave you unitization there. This is the same as that notation where you just use that. And oops, this is the same as so using these open brackets here, sorry, meant I didn't include the endpoints. Using the closed brackets means that I did use the endpoints. 64. That is correct. The infinities are always open because they're not part of the real numbers. 64. Close interval, -8 to 4. Union close interval, 4, 10. And so I have here -8, 4, 10. And so I have the close interval from -8 to +4, and the close interval from 4 to 10. Therefore, the union of those, includes everything from -8, including 4, because they both include 4, up to 10. And so your answer is the closed interval from -8 to +10. The number would not be included if you have an open circle or a uh, parentheses. So parentheses means you do not include the endpoint. Okay. Let me do problem 66. The closed interval, -1, 2, union, open interval 2, 6. So I have here -1, 2, 6. So I go from -1 to +2, and from 2 to 6. So the union will be, well, I start at -1, I go to 2, so I've included 2, and then I keep going to 6, but I do not include 6. So notice that the 2 was included because the 2 was included in this first interval. Therefore, it is the half open, half closed interval from -1 to +6. Let me do problem 68. -4, 6. Closed interval, -4 to 6. Union the closed interval, -1 to 1. And so I have here -4, -1, 1, 6. So I go from -4 to +6, from -1 to +1. So the union of these two sets is, well, everything from -4 to +6. And so that's your answer. -4 to +6. Yep, it'll be all numbers from -4 to +6. Correct. Okay. Problem number 70. Closed interval, 3, 5. Union, closed interval, 4, 10. And so 3, 4, 5, 10. So I go from closed interval from 3 to 5, closed interval from 4 to 10. Therefore, the union will be everything from 3 to 10. Yes. 72. The open interval from -infinity to 7 intersect open interval 4 to infinity. And so 4, 7. And so let's do the open interval, -infinity to 7. So everything less than or equal to less than 7. and 4 to infinity. Everything greater than 4. So let's find the intersection. So that'll have to be the overlap. So what's in both sets? Well, what's in both sets is actually the open interval 4 to 7. Yep, so they should be they are open circles, correct. So in this case, it is the open interval 4, 7. $74 to infinity, close interval from 2 to infinity, intersect the close interval negative infinity to 3. Yep, the infinities are not included. And so, yes, I have 2 to infinity. Oh, we'll do that. And everything from negative 3 and below, from positive 3 and below. And so the overlap is just the close interval from 2 to 3. And the last one was negative 100. Okay, so example. So negative 50 to infinity intersect negative infinity to negative 100 or positive 100. Oh, 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 okay. So let's, instead of infinity. Oh, instead of infinity. Okay, so let me do this, do that one. So, uh, negative 54 for infinity. Oh, wait, well, you can't, you have to have a positive 100 because that doesn't make sense. Okay. So this is what you mean, correct? Okay, so let's do this. So negative 50 for 100. So we'd go from negative 50 to 4, from 4 to 100. And we want to find the intersection. Well, the intersection is going to be nothing. There's no intersection here because they would try to join at 4, but neither of them include 4. So there's nothing there. So nothing. So in this case, it'll be the empty set. That's right. So since the first number is not included. So since the 4 is not included in this set negative 50 to 4, and the 4 is not included in the set 4 to 100, then there's no overlap. Okay? That is correct. You do not include an endpoint if there's a parenthesis. You do include it if there is a bracket. Okay. Let, actually, let me do that. Let's do this. So if we did this intersection, negative 50 for 100, well, it goes from negative 50 to 4, and from 4 to 100. Again, your answer would be nothing. Because note that even though the 4 is included in the first one, the 4 is not included in the second. Yep, that is correct. And so, because it's not included in both, then the intersection is nothing. No intersection. And so your answer is the empty set yet again. Okay. Let me do 76. Negative infinity to 9 union to infinity. Okay, so let me do that. To 9. So negative infinity, and we include the 9, 2 to infinity. So let's find the overlap. And so the overlap is from 2 to 9. And so it's the closed interval from 2 to 9. Okay? Difference and complement. So first, universe. So every set is a member of a universe. And so the universe is a collection of all possible sets. Please note that a universe is not necessarily a set. Is may not is not necessarily. It might be a set, but it might not be a set. Difference. So A take away B. Sometimes also denoted A minus B is just the set of all x's such that x is in the set A, but it is not in the set B. Try that again. Okay. And so say we have the set A, and I have the set B. And of course, we're in some universe, but doesn't matter. Yeah, I'll put the universe here for the heck of it. And so Yeah, maybe. So, oops. Let me make it a little smaller so I can. Oops. So union is it looks like a U, correct? So let me just so this is I have to sort of fill this in okay, as best I could, I guess. Okay, so that is A without B. Okay, so it's everything in A, but it is not in B. Now you could do it the other way. A. So this means B take away A. So it's the other part. Complement. A complement, sometimes denoted by a little dash, or this, or that, or this, or that, or not A. Um, those are probably the most popular notations for complement. And so this is just a set of all x's. And so this turns out to be the same as the universe without A. It is the set of all x's which are not in A. Yeah, all those mean the complement. That's correct. So um, I could use any of those to mean the complement. So let's say this is the universe, and let's say this is A. Then all this stuff out here is the complement. Oops. Oops, forgot to change the pen size. So this is the complement of A. All that stuff out there. So it's say that the set A is the set of all students that are going to get an A in the class. Then the complement of A is the set of all students that are not going to get A in the class. It's the opposite. It's what's not in the set. That is right. It's everything outside of the set. Of course, you always have to be in your universe. So no matter what, when I'm talking about anything, your a set must be in a universe. So it's understood that it's in a universe. Okay. So let me do some examples. Let's say problem number 77. Darn. 77. The universe is the set 1, 2, 3, up to 10. And the set A is 1, 2, 3, 4. The set B 2, 4, 6, 8, 10. First, compute the complement of A. So what is not in A? Well, the things that are not in A are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That's what's not in A. 2, what's not in B? So what's not in B are 1, 3, 5, 7, 9. 3. A union B, complement. So first let's figure out A union B. So what's an A or B? So it's 1, 2, 3, 4. 1, 2, 3, 4, 6, 8, 10. Let's find what's not in that set. 1, 2, 3, 4. So 5, 6, 7, 8, 9. 5, 7, 9. 4. Let's find the intersection between the complement of A and the complement of B. And so we already calculated that in the first two of these. And so, what's in the intersection? Well, there's a 5, there's a 7, and a 9. And that's your answer. 78. Let's do 79. Union, the universe. So the universe, 1, 2, 3, 4, 5, 6. A is the empty set. B, 1, 3, and 5. So let's do the first one. A complement. So what's not in A? Well, it's the null set. So everything is not there. So 1, 2, 3, 4, 5, and 6. Uh, what is not in B? Well, everything except for 1, 3, and 5. So 2, 4, 6. 3, A union B, complement. So A union B, well, A is the empty set, so it's just B. 1, 3, 5. And so what is not, well, that's got to be the same. That's not in B. So 2, 4, and 6. 4, the intersection between what's not in A and what's not in B. So what is not in A? Well, everything. What's not in B? Well, 2, 4, and 6. And so 2, 2, 4, 6. Okay. Okay, good. Cartesian product. So the Cartesian product between the sets A and B is a set of ordered pairs, A, B, such that A is in the set A and B is in the set B. And so, note that the Cartesian plane is just the cross product between the real line in itself. Properties. So let me give you some properties of so this is the Cartesian plane. So it's the Cartesian plane. So note that the Cartesian plane is sets of ordered pairs, which is just, I call them A, B, you could call them X, Y. Okay? Let me give you some properties. The commutative properties. So again, suppose A and B are sets, then A union B is the same as B union A. Similarly, A intersect B is same as B intersect A. The associative properties. A union B union C is the same as A union B union C. A intersect B intersect C is the same as A intersect B intersect C. Distributive properties. A intersect B union C is the same as you can figure it out without memorizing them, but uh, they're really the same. In other words, it's the same as 5 times 4 equals 4 times 5, right? Uh, if you use the old notation for, union, and for intersection, they just look like all the normal properties you always had. So you don't really have to memorize them uh, if you if you just use all these old notation. It just looks like indifference is minus, or complement. Let's say complement. The complement is the minus. You everything just looks the same way you've all seen things for numbers. So it doesn't really give you. So you really don't have to memorize them. They just all look like all the properties you would normally have for numbers. What is the most common? Oh boy, I don't know. Uh, I keep switching. Sometimes this little dash here, but the C, I would say probably the first. Well, I don't know. They're all used about the same amount. Uh, which ones? Maybe the first, second, third, fourth, and this one. So maybe these two are not as common as the others, but they're used just about. I would say that you're going to see them almost in equal quantities, and even in the same book, and even in equal quantities. We tend to switch back and forth between all these notations. Yeah, um, yeah. So distributive property. So we have that intersection distributes the intersection distributes over union. So A intersect B union A intersects C, and that union distributes over intersection. So A union B intersects C is A union B intersect A union C. And this is usually sometimes called the property of one with real numbers, or, well, this is actually called the fact that they're idempotent. A union A is A for all sets A, and A intersect A is A for all sets A. The other one, oh, the identity properties. So the existence of additive and multiplicative identity. And so A union, the empty set, is A. You know, A plus 5 plus 0 is 5. And A intersect the universe is A. Again, 5 times 1 is 5. So those are the existence of your identities. You also have the, um, well, inverse, but usually these are, so this is the complement rules. Uh, but back when we did these in the first day of class, we call these the inverse properties. So A union, the complement, is the universe. Well, no, actually, let me do it. Let's do it with the empty set. Um, okay, so that's the universe. And A intersect, the empty set, is the empty set. Okay. Um, well, again, the complement the opposite, the complement of the universe is nothing, and the complement of nothing is the universe. Okay. And well, if you have two negatives, they cancel out. The opposite of the opposite is the original. Okay. Oh, and I guess you should note the following. This is the same as A intersect the complement. Okay, right. Okay. Um, oh, the absorption. Yeah, I should probably have those. These are called the absorption laws. A intersect A union B. Well, what's the overlap between A and anything that, oops, includes A? Well, it's going to be A. And similarly, A union A intersect B, that'll be A. And so, yeah, these are usually the property of, so the property of zero, universal bounds. A union the universe is the universe. Let me make that so it looks like let's make my universe, I'm going to make my universe a fancier U because it's so that people can see its universes and not U's. So let me just make a quick little universe. So let's make those nicer, or U's that look not like. See, oh, there's another universe. So you can actually see that they're universes and not unions. Oh, there's another universe. Okay, good. So just makes it look like they're not universes, that they're not unions but universes. Uh, if you intersect anything with the empty set, well, the overlap, of course, is going to be the empty set. And this is actually what we saw in the very last problem that we did. Sometimes they call these De Morgan's law. The opposite of union is intersection, and vice, and so. Yep, A union universe is universe. That is correct. And so A union B complement is the complement of A intersect complement of B. And A intersect B is A complement union B complement. That's right, because they have nothing in common. Correct. That is correct. Okay. And let's see, did I give the complement? I may have given the complement laws. Yes, I did. Okay. So those are really about it. So that's really about it for all of those. Um, Maybe let me just do one quick thing. Um, oh, well, we did it. Ah, notice if I look here, A union B complement, and just bring the complement inside, so that complements that gets A complement, changes union to intersection, and B complement. Notice I got 579. Oh, when I did it, I got 579. And let's look for another example. Well, in this one, notice I have the complement on the outside, makes that a complement, changes union to intersection, makes that a complement. I get the same answer. And so notice that I did this in these problems 78, 77 and 79, and I got the same answer. Yeah, so what you do is you just change, and so basically you take the minus sign and you just put the minus inside, change all the signs, and then change this operator from whatever union, interchange them between unions and intersections. And that's how it always works. So it's actually kind of an easy thing to remember. Okay. Suppose I wanted to show one of these. Let's just show. Um, let's show this first one here. And so I'm not. I'm just going to do one of them. Um, prove. So example. Prove that. What did I say? A union B is the same as B union A. Okay. So let's show that. Okay. Let X be a member of A union B. Then X is a member of, well, let's see what A union B, set of all X such that X is in A and X is in B. Okay, so X is in A or X is in B. So that says, so X is in A or X is in B. So X is in B or X is in A. And so X is a member of, well, the set B union A. So that says that A union B is a subset of B union A. So now let, I don't know, Y be a member of B union A. Well, that's what we're trying to prove, and that is correct. So it shouldn't make any difference. So that's what we're trying to prove. So then y is a member of B, or y is a member of A. So y is a member of A, or y is a member of B. Therefore, y is a member of A union B, which implies that B union A is a subset of A union B. And so since A union B is a subset of B union A, and B union A is a subset of A union B, then that says that A union B is the same as B union A, and you are done. Okay? And so all the other proofs would be of a similar fashion. And so, well, not all of them, but and so that's an idea of how you would show it. Okay? And that's really it for today. So if you have no other questions, then I guess I will see you in over a week. Okay. Um, okay then. Bye bye now. I'm going to be removing everyone.